Hello, welcome to the last plenary session. So we have a pleasure to start with the Tycho Brahe Medal Award. So Tycho Brahe Award is awarded in Tycho Brahe Medal is awarded in recognition of the development or exploitation of European instruments or major discoveries based largely on such instruments. So from 2008 to 2011, the EAS gave an award, and since 2019, EAS awards a medal. So this year, 2024, Tycho Brahe Medal is awarded to Professor Francesco Pepe from University of Geneva for the development and exploitation of ultra-stable high-resolution spectrographs, which revolutionized detection and characterization of small mass exoplanets. So please, Professor Pepe. And now, please.
So thank you very much for this great honor and pleasure for this award, this medal. It's also a great pressure because when you get such an award, you are implicitly compared to great people like Tycho Brahe in that case. So it's a pressure because I think that these are people who did fantastic things. But I had the chance to have a neighbor, Professor Michel Grenon, who came to me and he said, don't worry, you know. Yeah, there is somebody who probably, I don't know whether you know this guy, Francesco. It's a Swiss. It's Joost Bürgi. He's from Thurgau, very close to where you were born and so. And actually, it seems that he did a lot of work to improve Tycho Brahe's instrumentations, and also he helped Kepler as a mathematician. He was also a mathematician and watchmaker, this Joost Bürgi, to do the work by Kepler. So this somehow relaxed me because, a Swiss has participated in his small own contribution to greater works. And what do we learn from that? I would say that the first, of course, that Swiss are very good in making watches, as you know, and besides cheese and chocolate. But also, and more importantly, is that the rarely discoveries and progress is made by one single person. So we all are called to contribute with our own good work to these progresses. You probably know all about that discovery in 1995 by Michel Mayor and Didier Queloz about the first exoplanet ever, about around 51 Pegasi. And at that time, I was actually very young postdoc. I just finished my PhD thesis in Zurich. I was doing balloon flights. I was building a far-infrared spectrograph, a small helium liquid-cooled spectrograph in competition with the ISO satellite, but of course much, much smaller and on balloon flights. But I was very much interested by the discovery. And as an instrumentalist, I was actually flabbergasted because for me it was something that was almost impossible. How did they do this discovery, considering that they were using the Doppler effect to see the motion of the star of a 1.5 million kilometers big fireball boiling at its surface with a precision of, let's say, 10 meters per second at that time, which is actually, if you look on the spectrum, on the detector itself, it's a motion of the spectrum of the order of 1/100th of the width of the stellar lines. And it's a 1 part in 10,000 of the width of, or the other way around, 1 part in 1,000 of the width of the spectral line and 1 part in 100 of the width of the pixel, of the detector pixel. And an instrumentalist, I was just flabbergasted. It's not possible. You cannot go so much below the spectral resolution. So I was fascinated by that. I continued my postdoc in building a liquid helium-cooled spectrograph, and at some point, I had the chance to be called by the Geneva University because they wanted to continue these balloon flights. Actually, or at least that was the intention initially. So I was called in 1998 to this observatory that had made this great discovery. But the situation was not very nice at that time. Switzerland was, we are very slow in Switzerland, but for once we were in advance with respect to Brexit and others. We just had the referendum about whether to enter in the European economic space, and it was rejected. So but at the same time, we had the chance to be in ESO, and so there was this beautiful vignette here about La Suisse participe, Switzerland participates to the very large telescope. And you see with this, you can see stars that are billions of light years away from us. So that was the situation. I was coming to the observatory and had this chance to come in a very dynamic environment, being also part of ESO, access to instrumentation. And what happened is that at the same time, there was a call or an announcement of opportunity by ESO after the outcome of the working group ESO La SIA 2000 plus, where they actually had decided at ESO that ESO needed to have a machine to do 1 meter per second precision and put on the 3.6 meter telescope dedicated to exoplanet search. And they would be ready to put 100 nights per year to this experiment for 5 years. This was the first and a unique announcement that I would consider it as a vision because it triggered then all the work that has been done. What was the science case? Actually, very simple. That's more or less the summary of the exoplanet field in 1999, where you see there were a few exoplanets known, mainly Saturn and Jupiter mass on relatively short orbits. No sign of Neptune mass, sub-Neptune mass, or super-Earth or Earth planets or Earth mass planets at that time. So there was a clear necessity here. And you also can see that lowering the threshold from 10 meters per second, that was typically the precision we would achieve at that time, to 1 meter per second would open this discovery space of lighter planets. So that was the starting point, and I was kidnapped by Michel Mayor because I was the only, I was just there. I was supposed to do balloon flights, but they told me, Michel told me, no, forget about balloon flights. This is old. Now you have to build a radio velocity spectrograph. I had, of course, no idea of how to build a radio velocity spectrograph, so I had to develop some kind of strategy. And the approach was the following. Of course, it was an approach that I developed in this group, helped a lot by Michel himself. And I would say these are the 5 main points of this approach. And the first one is what I said before, a decision, a vision to dedicate 500 nights to a program, a comprehensive program. I mention this because when we answered the proposal, there was a large fraction of the community which thought that this was just too generous. Why giving 500 nights to a single group or a single consortium to do this program? So I was in Michel's office when he got an email during the decision of the ESO Council. They actually called. So Guy Monet at that time, head of instrumentation, he called on behalf of the ESO Council and said, "Look, Michel, they don't want to give you 100 nights. Are you happy with 50 nights per year?" So we looked at each other in the eyes, and then we said, no, with this, we will not be able to do the program. So he said immediately to Guy Monet, sorry, either 100 or then we just let it be. You will find somebody else to do the instrument. 2 minutes later, he got a call back. ESO had decided, it's okay, you get the 100 nights per year. This was fundamental. This was fundamental together with the precision goal of having the 1 meter per second and having high efficiency to do this work. So my work was then to understand what were able to be done, because we were crazy. 1 meter per second was basically 10 times better than what we were able to do at that time with Coralie. So I went to the Coralie spectrograph on the Swiss telescope you see in the middle picture, and I tried to understand what can we achieve today. And astonishingly, when observing with Coralie here in the middle panel, we could actually see that if we were looking at the 2 different fibers feeding the instrument and trying to check how precise can we get differentially between the 2 different fibers, then we could go down to 10, 20 centimeters per second when integrating and binning. So Coralie already confirmed that it was possible to go to the 10 centimeters per second precision if you do things right. The other approach, and this was also in collaboration with ESO, was the awareness that an instrument is not only hardware. The data reduction pipeline is part of the instrument. So they asked us to build an integrated data reduction pipeline which would deliver science-ready radio velocities and spectra. And so we went for this approach, and we decided to improve whatever we can, reasonably can, of course. And so we decided to go for a very stable spectrograph in vacuum, temperature stabilized, and so on. And of course, building up a team, because nobody can do an instrument by its own, a team of motivated people who all knew in which direction we were going to work. Makes this sense? I think so, but not everybody was convinced. So I have just, while preparing this talk, I was thinking back at the IAU meeting in 2000 in Manchester, and the sentences I actually heard when we presented the concept of ARBs. Okay, so look, simultaneous reference, the technique Michel Mayor is using here, doesn't work. You have to go for the iodine cell. Okay, forget about simultaneous reference and Torrey Margin. Or your instrument is too expensive. Why do you want to put it in vacuum? Just take whatever spectrograph. And anyway, you will never reach 1 meter per second, with your technique. In any case, what for? There is no need to go for 1 meter per second. The stars will limit your precision to 3 meters per second, so just forget it, okay? And last but not least, planets are rare. There are only, okay, we just found Jupiter mass planets and Saturn mass planets, and it's maybe a few percent, so why you do all this effort? This is real. This is what was being said in 2000. So we decided to proceed because we had very clear ideas, and we built HARPS. It's a 5 million euro project. It was by 3 days shorter than 3 years, the total duration of the project. And it involved 5 partners, including ESO, having an active role in constructing this instrument. And these are a few results of the first slide and the very early days. For example, you see on the top panel in the center, pulsation P modes in the rate velocity of individual star. You can see them by eye. You see the oscillations of 5 minutes, a little bit shorter, a little bit longer, depending on the stellar type of this, just by having precise radial velocities. The middle panel shows an orbit of a planet. It looks like a binary star, but actually it's just 1,000 times smaller in amplitude. But the precision of the data points, when you have the precision. And of course, the efficiency, a key component in this, because it doesn't really help if you lose all the light delivered by a 3.5 meter telescope just in the fibers or in the instrument. I don't know whether there is sound, probably not, but I wanted to show this video. This was during the first slide, where Michel is explaining to Didier and to the journalist. You see, okay, this was first slide. You see, with this instrument, we are going to revolutionize the domain of exoplanet, because with this 1 meter per second precision, we will find planets that are not yet known today. And so in 10 years, we will have hundreds of low mass planets that we don't know today. And that's exactly what happened. The first was Mu-Ara A. What you see here, it's an astroseismology campaign to the right on Mu-Ara, because it was known to have a Saturn mass planet on a longer orbit. So we did astroseismology campaign. And here you see just 8 consecutive nights with each 700 data points per night to do astroseismology. But then when you bin these data points, you see immediately that there is, in addition to the long period, there is a short period, a 10-day period planet of only 10 Earth masses. This was the first super-Earth, or let's say sub-Neptune mass planet discovered in 2009. And this was the start of the era, of a new era. So I call it a turnover in the domain, because if you look at on the right side, on the bottom side, these are screenshots of radial velocity curves of the stars in the sample in 2007 that Christoph Lovis, just before going to the conference, he just printed out all the radial velocity curves. And we found out that all the stars have at least, basically all the stars have at least one planet, if you look with sufficient good precision to them. And so this was the start of the statement. Actually, almost all the stars have exoplanets. Oh, okay, then I have to accelerate. So this was the situation in 2014 with 51 Pegasi discovered in 95, Mu-Ara D in 2004, and you see here the masses, the minimum masses detected by the different, by increasing the precision of the instrument. And there is Alpha Centauri BB, which turned out not to be a planet, but the amplitude was of much less than 1 meter per second, and the equivalent mass would have been 1 Earth mass. So that was the situation. But we had to do more, and because we wanted to find Earth mass planets as well. So here you see the amplitudes expected, for example, for an Earth on a 1 AU orbit would have been 10 centimeters per second. So we had to work in this direction. And there are different things we have been working on and we are continuing working on, from photon noise, of course, increasing the spectral resolution to get preciser measurement, instrument stability and IP knowledge to get accurate measurements, the wavelength calibration as well, other contaminants, and stellar effects. I would say this is probably, this latter one, is the most challenging and limiting effect today in observing Earth's mass planets. But we have a strategy, and the strategy is to understand the star, because what it looks to be as noise, if you have the photons and if you have the instrumental stability to measure it, then it turns out into a signal. And the signal, external signal, you can model and you can correct for it. So understanding our sun is the first step, because this is the one we have most photon and we know the best. So here you see the solar telescope on Harps North. Basically all EPRVs today have a solar telescope to study the sun. And why I'm mentioning that is because these are the raw data, but when then you combine that with data processing, with very sophisticated data processing, then you can reach on our sun, which is not the most stable star, you can reach centimeters per second long-term precision, and this you can also do on other stars. So here, this opens really the path to the detection of Earth's mass planets and Earth's analogs. So we build Espresso because you need also an instrument. You need an instrument like HARPS, or better than HARPS, on a bigger telescope because spectroscopy is photon starving. So we built here Espresso, high resolution, high accuracy, high stability, and so on. Very quickly, because time is running out, that's the just one example, Proxima Centauri b here, and D, which was discovered with Espresso. In continuing observing Proxima, we found out that there is a force of an Earth mass planet around Proxima. So again, it's not a solar type star. Okay, it's a much cooler star, much smaller star, but still one quarter of the Earth's mass that could be discovered or detected with Espresso. So that's the situation today. That's where we are. Proxima Centauri D, it's much less. So we are still continuing progressing in this precision. Oh, yeah. This is just to say that there was a second turnover and a third one. The second was that when you have a EPRV spectrograph, you are not going to do only blind search. You can combine these radio velocities with transits, and so go into the interior of the planets. Here you see the combination of different projects, ground-based EPRVs and satellite transit missions. And here the contribution of Espresso and Harps North has been really dramatic. If you look at this case here, we are in the sub-Venus mass. When you know the period, then you can go even deeper or even more precise because you remove certain free parameters. And that's a summary of what Espresso, Harps, and Harps North have contributed to the precise mass determination. The other aspect is that when you have a spectrometer, and if you look only at the radio velocity, this is a very reduced observable. From millions of channels, you reduce to one. But there is much more information in the spectrum, so you can use that, for instance, to do transit spectroscopy. We started with that with HARPS. Yesterday you heard a beautiful talk by Julia Seidel using the four UTs with espresso. This was the first discovery with the espresso WASP-76b, where we could see a difference between the egress and the ingress and the egress in the transit spectrum of WASP-76b, which then revealed us that this planet has rain, iron rain at the terminator between the day side and the night side. Fantastic thing. And if you put then four telescopes together, you can go much, much further in sensitivity. So a summary, I think that the HARPS or instruments like HARPS and Espresso have a legacy of high fidelity spectroscopy, not only for the blind search, not only to go for Earth analogs and maybe find candidates for future missions. Thanks to this, what we contributed is this instrument suite of HARPS. There will be 3 in the sky, Espresso, but also in the near-infrared with NIRPs. The combination of transit mission with rate velocities and spectroscopy. And here we are really looking forward to the Plato mission and what the combination of these two techniques can bring. And then, of course, spectroscopy of atmospheres, of exoplanetary atmospheres. And I'm sure if I had to bet today, I would say that it will be instruments like ANDES and the ELT, which will find the first, hopefully, biosignature, if there are any, around other worlds. So that's the conclusion of my presentation. I leave you with my 7 golden rules for young people. If you're interested in, I think, what can be done right or what can be done wrong, it's not only about technique, it's much more than that. And it's really important to keep the effective science goal in mind when taking decisions. Thank you for your attention.
Thank you very much for this great talk. We have time for one question, if there is one burning question from the audience. I don't see any. Then, oh, is there? Ah, okay, Tony.
Just one. So what's next?
Yeah, I think what I just said before is, to me, there are colleagues taking over. We are working on Ristretto, which is a spectrograph that will combine high spatial resolution with high spectral resolution, trying to find maybe oxygen around Proxima. But the next step is then in spectroscopy, of course, because there are many other things. It's ANDES. ANDES with a 40-meter telescope and a high-resolution spectrograph. I think this will be really fantastic. It's like putting glasses on. If you are, short-sighted, then you put your glass on and suddenly you find out a new world out there. I think that this will be the next steps. But of course, if you look at other techniques, is much more to do, and the combination with Plato will be also a fantastic new step in this domain.
Okay. Thank you for amazing instruments and discoveries and exciting times ahead. Thank you. And now I give the floor to Tony, who will take over.
Okay, thank you. So we continue this session with some reports, and the first one is going to be the ESA Science Program Highlights and Future Directions from Gaitee Hussain, who is the Chief of Science. Was it correct?
I'll explain.
He will explain. She will explain. Floor is yours.
Thank you. So, yes, I'm the head of the Science Engagement and Oversight Office, which is a newly created office at the European Space Agency Science Directorate, and it aims at engaging actively with our scientific communities and working with our scientific advisory structure to ensure that we are serving your scientific priorities and ambitions, and across multiple disciplines. So I'm absolutely thrilled to give this update for this particular meeting. It has been a phenomenally busy and productive year, so it's been somewhat challenging to identify which highlights to focus on in this talk, but let's give it a go. Before I do so, however, I just wanted to give you a very brief introduction to the European Space Agency for those of you who might be a bit less familiar. So the European Space Agency is constituted through the funding and support of 22 member states. As of the 1st of January next year, we'll actually be 23 member states with the accession of Slovenia, thanks to a recently signed agreement. It consists of roughly 5,000 employees, half of which are staff and half of which are actually employed by industry across the ESA member states, but locally contracted on ESA sites to work with the staff every day. There are headquarters in Paris, 7 sites across Europe, and we have the spaceport in French Guiana, which in a handful of days should see the inaugural launch of the Ariane 6 rocket, which has been highly anticipated and is very important for Europe's autonomy in reaching space. Now, the original purpose of ESA, it's almost exactly 50 years old. Next May, we will celebrate its 50th anniversary. It was formed to essentially enable Europe to explore and use space for exclusively peaceful purposes. In particular, what we aim to do is empower Europeans to develop and maintain leadership in the space sector. This is a sector that, of course, is extremely dynamic and rapidly expanding. And so the activities of ESA cover many different areas, from navigation, transport, to the program directorates, which are focused on building scientific missions, but also exploration missions. So we have the Earth Observation Directorate, which, as the name would suggest, produces satellites that monitor the Earth intensively for scientific, political, and industrial and business stakeholders, with a real focus essentially of following also the impact of climate change to allow decision makers to make responsible decisions. In the Human and Robotic Exploration Directorate, we have, as the name would suggest, the astronaut program, as well as missions planned for, experiments planned for the International Space Station, missions planned for low Earth orbit, as well as the Moon, and then subsequently Mars. The 2024 budget was 7.79 billion euros. If you divide that amongst the 450 million European citizens, then that averages out at 17 euros per European per year. That corresponds to, we like to call it, the price of a cinema ticket. The science program within that is 600 million euros. So that comes out at just over €1 and something per European citizen, so maybe a chocolate bar. And for that money, let's talk about the Science Directorate. With the Science Directorate, we work very closely with the scientific communities to identify your priorities, work with industry across the member states in order to deliver on your ambitions. The range of scientific areas that we cover are pretty large. They cover heliophysics, planetary science, astronomy, and fundamental physics. These are, of course, very broad topics, and within them we contain multitudes of scientific communities and disciplines. You can divide up our missions into 2 separate fleets, the Solar System Explorers and the Cosmic Observers. And I think there are still some posters of these left on our booth, if you want, after the session. Now, along the top, you can see the missions that are still in development. Along the middle, you can see the missions that are currently actively in operations and that are gathering science data. And along the bottom, you can see the missions that have completed their missions. They are literally resting in various parts of the solar system, having delivered their data into our archives, where they live on to serve future generations of scientists who can bring new data, new models, and new insights to data that was acquired, in some cases, a few decades ago. The missions that we currently have in operations got a new member in the last year, with the commissioning of JUICE ending successfully. JUICE is, of course, now on its long cruise phase to the Jovian system. It'll arrive there in about 7 years' time. But along the way, we're using the opportunities of flybys to check out the instruments, calibrate, and see if we can do some opportunity science along the way. The next mission that will be joining this fleet will be Proba 3 with any luck. It'll be launched from India. It is a mission that's actually led out of our technology directorate. It's a technology demonstrator, and it's aiming to do solar coronagraphy. So there's a scientific element to it. The cosmic observers cover the entire range of the electromagnetic spectrum and actually beyond, with the recent adoption of the LISA mission, which is probing gravitational waves and essentially ripples in space-time. So you can see, as before, the missions that are in legacy are along the bottom. They've already delivered their data. In the past year, the missions and operations have been heavily added to with the addition of Euclid and partner-led missions XRISM and Einstein Probe. And so Euclid is, of course, ESA-led, XRISM is led by JAXA, and Einstein Probe is led by the Chinese Space Agency. And so there's a lot more to say about that, and let's get to the highlights then. So around this time last year, when you received the last ESA Space Science update, we had recently launched JUICE. It was undergoing commissioning, and Euclid had just launched a few days before the EAS. In the meantime, both spacecraft, both missions have been successfully commissioned. We have started acquiring data. Of course, as with every new instrumentation, every new mission, there have been challenges. In the case of JUICE, for instance, there was the deployment of the RIME antenna, which took a little bit of work, but we got there. And with Euclid, we have ongoing, we're trying to understand the ice decontamination procedures, which we're having to do regularly. However, we have limited time, so I will focus on what we've been doing in the last 12 months in terms of science. So between commissioning and the start of the survey, thanks to an ESA-led and Euclid Science Team-led initiative, we agreed that we would spend 24 hours of clock time, essentially, of Euclid observations. We invited the Euclid community and interdisciplinary scientists to submit cases of fields that we could observe, with the idea that the data would be made public to showcase Euclid's capability and enable scientists and enthusiasts worldwide to benefit from this remarkable mission. So in November last year, we had the first release of the images that came out of that early release program. And the fields that were chosen were deliberately chosen to target vastly different kinds of fields. So we could target different kinds of objects, from local star formation regions, like very famous star formation regions like the Horsehead Nebula, and then going further and further to different kinds of galaxies and clusters of galaxies. Almost a couple of months ago, we released the second lot of Euclid images as part of this early release program. And here again, there are a diverse range of astronomical and cosmological fields that were targeted. In addition, with this latest release, there's public data sets that are available to all of you to download if you have a few hundred gigabytes free. And you should actually, I encourage you, if you haven't already, to explore these images, because you can just keep on zooming in, and you just have remarkable levels of detail. Now, the really nice thing so Euclid is now embarking, and I can't move this on, okay. So Euclid is now embarking on a 6-year survey. And of course, the aim is that this is an extremely effective dark matter and dark energy explorer. So it's an enormously ambitious survey involving literally thousands of astronomers from across the world, but particularly in Europe. And so what was really nice to see in Able 2390, which is this massive galaxy cluster, which this one image captured over 50,000 galaxies, is you can zoom in and hopefully you can see this. Oh yes, I just wanted an excuse to show this on the really big screen. You can see these arcs of these telltale signatures of strong gravitational lensing. Of course, we'll be looking for weak gravitational lensing as well, and looking at galaxy clustering and how that evolves over time. So another remarkable result that's come out of the early release observations is the sensitivity of the imaging is so exquisite. Just by enhancing the image slightly, you can see this intracluster light, which actually also enables you to trace where dark matter is in this galaxy cluster. And again, I just wanted an excuse to show this. I hope some of this is being shown properly on the high resolution screen. And thank you. And so, we are extremely excited about what will be coming out of this. The first 10 scientific papers from those early release observations have been published, and there is much more science to come, I hear, from the ERO authors. And so I just wanted to remark on how fortunate we are that we live in a time that we have these three great facilities, Euclid, Hubble, and JWST, working at the same time. You can see their unique characteristics and capabilities with this image collage that was put together by our comms team, which shows the Euclid image of the Horsehead Nebula. You see an archival image from Hubble showing this very precise detail of the structure in a certain part of the Horsehead Nebula. And of course, then zooming in with Webb and seeing this illumination front and actually seeing very detailed structure. So, so they're extremely complementary, and there's a lot more to come. I'm not going to spend a lot of time on this. We heard a lot about what's coming out of JWST, thanks to NERSPEC and GTO time on this amazing facility. And of course, there will be a lot more to come. And over the course of this week, I've heard JWST in almost every session I've been to. So it is transforming so many different areas of science. One thing that I would like to remark on, that I meant to remark on, is that it's really good to see a high level of European participation. So European PIs typically get a third of the time on JWST in the last couple of cycles, and the publications also show a similar level of involvement. So with PRISM, I'm not going to spend a lot of time on this. You can just see that with the resolve spectroscopy, we actually can resolve a lot more details, resolve individual atomic species in the supernova remnant in the Large Magellanic Cloud. And you can see the previous observation taken by Suzaku before. So there's going to be a lot coming from PRISM, even though we're having challenges on the soft X-ray front. Gaia as well, I'm not going to spend a lot of time on. I think you see this every year. So the numbers of publications from our ESA-led missions are enormously successful. This is year along here, and each of the different colors represent different missions. Gaia is the biggest chunk. It continues to produce 1,600 to 1,800 refereed publications per year since 2019, and it is becoming an excellent discoverer of black holes, dormant black holes in our own Milky Way. So there's a lot more to come, and we're really looking forward to DR4 coming down the road. So I just wanted to spend a few minutes talking about the future. So we undergo every roughly decade or so, not always a decade, a consultation exercise with the scientific community requesting you to submit white papers or what your burning science questions are, where you see technology going, and where that interface is. And so you can see all of the seminal missions that have come out of the previous exercises. Horizon 2000 was back in the 80s. Cosmic Vision was carried out in 2000. And we're reaching a point where we can see the end of Cosmic Vision. So we conducted the Voyage 2050, which was the latest consultation exercise that essentially has identified 3 large mission themes that we're already beginning to examine, and I'll talk about more about that in a second. But we have to also complete, of course, cosmic vision. And so we have a Council of Ministers coming up next year. We'll be looking at our funding capabilities and the ambitions of our scientific communities to work out what kind of cadence we can deliver in terms of calls for particular medium-class missions and fast-class missions to the scientific communities. So we're working with our advisory body on that. We have this continuous bucket of missions. So this is a list of missions, again, against year. And in green, you can see the missions that are currently in operations. As of this last year, we have more missions running in operations than we ever have before. And 2 new missions have been added in development. That was LISA and Envision were adopted in January of this year. New Athena has been confirmed back into the science program thanks to huge efforts from the instrument teams, from the scientific community, and we're really confident that it's back on track, aiming for adoption in 2027 and launch towards the end of the 30s. In Voyage 2050, we're also making strides. We have down-selected 30 original submissions that we received from mission proposals. A couple of years ago, we've down-selected to 3, and by the end of 2026, we'll have down-selected to the final 1. And we're also started technology studies, basically looking at the first L-class mission of Voyage 2050. We've identified the Saturnian system as the likely target. And in particular, we think the biggest advances, thanks to an expert team, are with Enceladus. We have jobs coming up. In the next 12 months, there will be jobs coming up in astronomy and solar physics, and we'll also be looking for a position at Space Telescope for an ESA scientist working on Roman. So if you have any interest, feel free to reach out, and I'll tell you more about it. The ESA Research Fellowship Program is also a great start for people who want to build an independent research portfolio. So please go ahead and think about applying for it. The deadline will be round about August 15th, August 16th. If you're interested in the science program and you want to find out more about anything that I've been talking about, or even more about Voyage 2050, then there is a webpage. We recently did an online town hall where you could, we covered almost everything to do with the ESA science program. The recording is there as well as a presentation, so do feel free to check it out. You can subscribe to our newsletter, which comes out on a monthly cadence and advertises opportunities for you to engage with the science program. And we'll be advertising those job opportunities in the newsletter also. So thank you very much for your time.
Thank you very much as well. It was quite nice. We have a time for a question, maybe 2 quick ones, if not. Somebody? I don't see anybody, do you?
I don't see any.
Well, you feel free. There's still, the booth is still out. You can get in touch with the people from ESA. So the next one, I would like to invite the Director General of ESA, who is going to tell us about the program status and forward look. So Xavier Barcons.
Thank you. Thank you very much for not leaving before my talk. I couldn't miss to start this presentation with that image on my back. This was taken by an engineer in Paranal about a year ago, and this shows that for the first time in almost a century, Europe is heading towards leading ground-based astronomy. This is our big project. This is the ELT. I'm going to talk about it in a few seconds. Okay, so I think, okay, yes, right. So yeah, last year we again enabled more than 1,000 scientific papers being published out of our observations. I want to drive your attention to the last rows of this table that you can see on the right, which is the importance of the science archive that we have. About 45% of our papers make use of the Science Archive, and actually more than 20% of the papers enabled by ESO facilities only use archival data. We invest a lot of effort into this, and it really pays off, so we're very proud of it. I know Roland Bacon has left, but I think he showed something similar to this, showing the gigantic impact of some of our new instruments in the VLT and the VLTI and other facilities, comparable to the one that FORS and UBES had in the early days. So you can see MUSE really being a very, very important instrument nowadays, but also all the others that we're developing together with the community. And this is only to put this in the context of other facility, both in the ground and space telescopes that we have there. With that number, there's no way I can do justice and describe you what the scientific highlights of the last year since we reported to you have been. I just put together a collage here of a few press releases. They are meaningful to me, at least. I like them all very, very much. But of course, as I say, this is a measure in justice to all the other breakthroughs that have been achieved during the last year. Let me run through various things that have been happening and new initiatives that we have taken during the last year. In the La Silla Paranal Observatory, we have fully established now the double anonymous and distributed peer review system to review the flow of proposals that we have. I have to say that one of our VLT telescopes, the UT4, has an insane oversubscription fraction of order of 20 at the moment. I'll come back to this, what we're trying to do to mitigate that oversubscription. We're preparing to move to yearly calls as of next year. We had to develop a new scheduling tool that we're still warming up and to making it more robust, but I think this is working fine. What we cannot resolve is that there's no time for everyone. That's unavoidable. Actually, I also wanted to allude to transformation that we have started, especially in Paranal, to prepare for the operation of the ELT, that it's coming very close in time, only 4 years from now. We have put together this program called Integrated Operations Program, where we're trying to redefine the operations model, making it linear, remote to the extent possible, and still high performance. And we've started, of course, with the most urgent topics there, in particular the maintenance process for the ELT domain main structure. That it's, as you will see in a second, this is coming very, very real at the moment. This, as I say, it will be a sort of transformation on the way we have been operating optical ground-based telescopes. And I think this is something that we will all need to think about for the future. By definition, these facilities are in remote places, and we need to be careful about moving people, goods, water, electricity, and so on to such remote places for sustainability purposes. Okay, some updates about the instrumentation. ERIS is the new kid on the block. We fixed, I believe, everything that had to be fixed at the beginning of the year, so it's in regular operations. Our multi-object spectrometers, MOONS and FORMOST, will come up probably next year. Gravity Plus, it's progressing. It's a stepwise project. You've seen some fantastic results obtained with Gravity Wide, the first part of it. The adaptive optics system is already in Paranal, ready for installation. We're also ready to install the lasers for the other 3 units other than UT4. And importantly, we have started 2 phase A studies this year, one for Blue MUSE, which was the second highest priority of the VLT 2030 exercise that we did back in 2019. But importantly, we have started also phase A to equip one of the other UTs, not just UT4, with the formable secondary mirror. So we will have a second adaptive telescope, at least with a narrow field. That will hopefully reduce the oversubscription pressure on UT4, which is something that we desperately need. That's the panoramic view that we have now of the instrumentation in Paranal, what's coming up. Besides what I have already mentioned, there's the upgrade of FORS, there's MAVIS multi-conjugate adaptive optics instrument, maybe around 2030, and CUBES, the UV spectrometer, also on a similar time frame. Oops, sorry. So let me move to ALMA, our other big observatory in operation. We've made some progress as well there. About 40% of the data sets are now delivered to the astronomers without human intervention in quality control, and the quality is as good as it was before. That's great. We could spare this effort into other challenges that we have at the observatories. Again, oversubscription is insane. We're talking oversubscription factor of 8. And I'm sorry we could not clone ALMA, so that's something that we need to keep in mind when moving forward. We have started to allocate time to proposals that use both ALMA and other big facilities like James Webb Space Telescope, but also the VLA and the VLT. And we're making a few changes here and there. And importantly, of course, because of the high oversubscription, the community is making very good use of the archive. And today, about 30% of the science publications coming out of ALMA make use of archival data only. Development, of course, we're also thinking about this. And the major development program that we have agreed with the partners is this wideband sensitivity upgrade. This will be a 10-year development project. We need to build a new correlator. We need to build new signal processing tools. We need to build new receivers. That's a rather comprehensive program that is being formulated. Right now, it will be reviewed at the end of the year and hopefully be approved in April next year. One thing that the wideband sensitivity upgrade will do, not the only one, but this is very important, it's to make ALMA faster. So that means that we will attack in front the very high oversubscription. We will be able to do the same science with less time. There's additionally many other benefits of this program, but at the very least, we will enable a lot more science with it. Okay, so ELT, the Extremely Large Telescope, as I said, largest optical infrared telescope in the world, the only one that is fully funded and the one that is more advanced in its development. We're still scheduling our first technical light in 2028 and maybe the first scientific light very soon after. After experiencing all possible issues that one can have with the project, in particular for the site work of the dome and the main structure, we're back into business, full throttle. We expect to have the dome and the main structure finished and delivered to us by mid-2026. And you can see the some of the pictures. I know Michele Cirasuolo showed some of them already a couple of days ago. This is really breathtaking. Just to remind you, the height of this beast today, it's more than 60 meters, and when the doors are installed, it will be 85. So the diameter of the auxiliary building that you can see at the base, it's 110 meters. So it's a gigantic thing, but of very high precision, like a Swiss clock. So here's a recent photo from the inside. You can see the first pieces of the telescope there, the azimuth tracks, the Nasmyth, the base of the Nasmyth platforms, and even the cell of the primary mirror of this gigantic mirror of almost 40 meters in diameter. And yeah, I invite you to visit our website. There's lots of materials that you can see there that our communication team have prepared. We're also making very good progress with the optomechanics. This primary mirror will be composed of 798 segments, 1.5 meters across. All the glass blanks for all these and the spares have already been cast as of a week ago. Polishing is proceeding at a very good rate now. They're basically polishing a segment per day to better than 10 nanometers RMS. This is really impressive. We've got already 72 of them coated at the facility in Paranal, 62, sorry, and there's up to 200 on their way or being coated at the moment. We still have challenges. Our risk registers are never long enough, but we're knocking them down one by one, hopefully. M2, this is a more than slightly bigger than 4 meters in diameter. It's already polished, better than 60 nanometers all across RMS. Absolutely impressive. M4, that's a program, a procurement that we started very early on. It's proceeding at full speed. M5 remains the biggest technical challenge of the entire project. No surprises there. We're taking all possible mitigating actions. Instruments, I'm sure you've heard most of it these days. Metis has completed the final design review. Mikado is getting there. Harmony has some issues still that are being addressed. Morpheo lagging behind, but also moving towards final design review. I'm happy that a few weeks ago we signed with the president of INAF the agreement to move on with Andes that Francesco spoke about before, and Mosaic, we're also observing very good progress on the initial design and hope also to sign with them next year. Prefocal stations are being delivered already in September. Phasing and diagnostic station, this is an ESO internal project making also very fast progress after final design review. Schedule, I already mentioned. Budget, let me say that it's very tight. Don't ask me more questions about this. Very tight. Cherenkov telescope array, some news here as well. Paola Andreani is now our program scientist, liaising with the community on how to make best use of the 10% observing time that ESO will get out of hosting and operating CTA South, how we can make best scientific advantage of this together with our other facilities. Now, we're having an issue of legal nature about the legal entity that will build and operate CTA, which is CTAO ERIC. I hope that we will have a positive solution to this in the next couple of months. In our site, which is where the South Array will be hosted, the access road was completed, and we're about to place the contracts for roads inside the observatory foundations, connections to the power grid, and so on. So this is progressing, pending of resolving this legal issue that's been driving us nuts, actually. Some important changes recently. Michele Cirasuolo is no longer, since Monday, the ELT program scientist. He's now the optical and infrared instrumentation program manager. He started on this role on the 1st of July. Joël Vernet is the acting ELT program scientist until we recruit a new person. And also an important change in the La Silla Paranal Observatory. Thomas Klein is now the director of the observatory, reporting to Andreas Kaufer, who remains the director of operations at ESO. Those are two roles which are of very close impact to the community, and that's why I thought it would be helpful to announce them here. Okay, so I'm coming to my last minutes, and I don't want to miss the opportunity to explain to you what are we going to do in the future after the ELT. This is a process that our council approved about a month ago, and that I would like to take the couple of minutes that I've got left to explain how it's going to work. So first of all, we have now a full strategic framework at ESO, a mission, a vision, the values, and the strategy for the next decade. Those have been all approved by council. And in that context, we should start now to look at what will be the next program after we finish the construction of the ELT and we put it in operation. And the idea there is to identify this program now in a process that will last almost 4 years. But what we're thinking is about something that is transformational, that it's a facility, meaning that it serves multiple scientific purposes, and we should think about this facility being operational in the 2040s, not in the 2030s. This is, if you can keep these three concepts in mind, you will be in the right mindset. This new program could be a new telescope facility at an existing site, at a different site, a significant upgrade of an existing facility that is owned or co-owned by ESO. All this would be possible. But very importantly, our council has been very strong in stating that what has to be the driver here is the science. So we need to do this science exercise in the coming 3.5 years, identify which will be the scientific challenges in the 2040s, that ESO could help resolving by means of a new facility. And those will be the selection criteria: scientific drive above everything, capability of the organization to do this, to own the design, the construction, and the operation of that new facility. Sustainability, the 2040s, the world will be very different to what we see today. Institutional model, as I said, it can be an ESO alone project or in a partnership. And of course, the risks will also have to be folded in. But over everything, science is the driver here. This is the approximate timeline that our council has approved. It will start with a 2-year preparatory phase where we will trigger workshops and dialogues with the community about science topics, not about facilities. This starts with science. Then only 2 years after, we will launch a call for ideas that will be assessed. We will put together a senior science committee to help us with this. And finally, after all the assessments, we expect that our council will make a decision about the identity of this new program at the end of 2028. So it's not that we have a pile of money in front of us that we don't know how to spend. It's the other way around, is that we need to think what is the science that we would like to do in the 2040s, and then find a way to deliver it. So with this, I'm finished. Thank you very much.
Yep, thank you. Thank you very much as well. Anyone want to question the Director General?
That sounds a bit challenging.
Yeah.
I think Francesco has one. Oh, sorry.
Yeah, we have time for a couple of quick ones.
No challenge. First of all,
Yeah.
congratulations. I think ESO can be really proud of what ESO is doing, and this ELT is really amazing. So congratulations. And I have a technical questions. You mentioned, really technical, sorry. You mentioned the RMS of the secondary 60 nanometers, and we learned also from Michele that, okay, the segments are at 10 nanometers.
Yeah.
Is there a discrepancy, or is it, why is this like that?
I need to ask my systems engineer. I don't have it here. No. I think this is the target. In fact, I think we're going to achieve better than 60 nanometers RMS for the M2. We're probably having 40 nanometers inside. And in fact, some of the segments of the M1 are better than 10 nanometers as well. But those are the specs, 60 and 10. Yeah.
Thank you.
Just one more over there. Yeah, Nabila.
Thanks a lot for the presentation. I was wondering how the exercise that you're mentioning in terms of finding priorities interfaces with the activities of Astronet or other forecasting science activities.
So yes, there's not only Astronet, which we have been part of, but there's of course the national roadmaps that are ongoing with different timeframes and so on and so forth. So what we try to do here is to harmonize this science drive with the priorities that exist all around. But remember, we have 16 member states. So we probably have very close to 16 national roadmaps on top of Astronet and many other reference priority studies. So it is a tough call, but that's why we're taking years to do this, to make sure that we can align the wishes of the community with the scientific challenges of the 2040s. Thank you.
Thank you again.
Thank you.
Thank you again. And now another Director General, I'm feeling overwhelmed a bit, Philip Diamond, who's going to talk to us about the Square Kilometre Array Observatory.
Thank you very much. It's traditional, I think, to say at this point, I stand between you and lunch. So I'll be efficient in my, my presentation. We are very much the new kid on the block here in terms of intergovernmental organizations sitting under a treaty, a convention. Our convention was signed actually in Rome in March 2019, and the observatory, the SKA Observatory, came into being in January 2021. So we're only about 3.5 years old. Very much the younger sibling compared to ESO, ESA, CERN, the other big IGOs in Europe. And what we're doing is building and operating not one, but two radio telescopes, each of which independently is the largest in the world. Our membership is growing, and currently we have the 12 countries that you see listed at the top. As of 2 days ago, it was 11. But what I'm very pleased to say is that yesterday, India became a full member of the SKA Observatory, having gone through its ratification process. And we're very pleased to welcome our Indian colleagues. And you can see that the geographic range of the members of the SKA Observatory is different from those of the other European IGOs. And that reflects the fact that our telescopes are in countries that are different from ESO, so in South Africa and Australia. Germany is very close to finalizing its accession process. I would say it's imminent, really within the next few weeks. The legal processes are finished in the German parliament. We're waiting on the final administrative steps. France, we expect to become a member towards the end of this year, early next year. And you can see other governments are moving through the processes. So our mission is very simple. It's to build and operate cutting-edge radio telescopes, transform our understanding of the universe. But we're spending taxpayers' money, so we're very conscious of the need that we must also deliver benefits to society. And so that is a significant part of our program. So what is it we're actually building? Just very briefly on this one slide. I've said 2 telescopes. Together, they cover the frequency range 50 megahertz to at least 15.4 gigahertz, hopefully higher, depending on the performance of the dishes. So from 50 to 350 megahertz will be a low frequency array consisting of these log periodic antennas, the evolved cousins of the old TV aerials we used to have on our houses. And that is in Western Australia, will consist of 512 stations, each station containing 256 antennas spread in 3 spiral arms with a dense core across 74 kilometers. And then in South Africa, ultimately 197 dishes, including the 64 Meerkat dishes and the Meerkat extension that is being funded by the Max Planck Gesellschaft and ENAF and our South African colleagues. Very similar configuration, but spread over 150 kilometers. And the headquarters sits in the shadow of the Lovell Telescope at Jodrell Bank in the UK. We are also putting in place a worldwide network of what we call SKA regional centers. And this is how you, the astronomy community, will interact with the SKA through these regional centers. You won't actually, unless for very special occasion, visit the telescopes. They're in remote areas of the world, deliberately so, to get away from population because of radio frequency interference. Our total project cost for the first 10 years is 2.1 billion euros. Early science expected of order 3 years from now. And what you can't see at the bottom is construction complete in 28, 29. So that's the path we're on. We have 1,500 scientists working in our science working groups that you see shown on the screen there, covering a huge range of science, as one would expect for a mega facility like the Square Kilometre Array. I don't have time to touch on the science, but there is a side event which starts again at 3 o'clock. Already had a session this morning where some of these science topics will be touched upon. Our current status, we now have over 300 staff, starting from pretty close to zero a few years back, ramping up to what will be about 450, spread amongst the three host countries, UK, Australia, and South Africa, in those proportions. We're almost 3 years now after the start of construction. The large majority of construction contracts have been awarded with 761 million euros of funds committed, not yet spent. We're spending it like money's going out of fashion, but it is committed. And maybe I shouldn't say this, but the IAU General Assembly would love to show a first light image. Our construction strategy is taking full advantage of the fact that we're building 2 interferometers. So we are building all of the infrastructure for the entire, both telescopes. The costs of deploying contractors in these remote regions is such that that's the only viable strategy. So all of the buildings, the trenching, the roads, the foundations, etc., for the whole telescope is going in. And then we're putting on top of that the telescopes and the antennas and building the back-end systems and, of course, doing all of the software. We don't yet quite have enough money to build what we call the baseline design. We're about 15% short. So we have about 1.85 billion committed. Still not a bad number. But that means we've had to put in place what we call a stage delivery process, which will end up with 144 dishes, including Meerkat in South Africa, and 307 stations. And it's part of my job to be raising the extra money to take us to what we call the baseline design. And of course, to do that, we're pursuing new members and additional money from the current members. So just to give you a sense of where we are, I'll start in South Africa. And this is part of our team in our Cape Town offices. We currently have 45 staff there. It will ramp up to about 150. And as well as India joining the observatory yesterday, we had a major milestone, which was the first big lift of the SKA mid-reflector onto its pedestal. I don't have a movie yet, that hasn't been sent to me, but I have still photographs. So that's a 15-meter diameter reflector made by CTC 54 in Xizhuang in China, being lifted up onto the pedestal. That was a big moment for us. We did watch it, some of us watched it live yesterday morning as it was happening. And so there are many, many more of these to go. So that's a really exciting moment for us at the project. And the inner area you see there will be filled in with the other panels. This is our construction camp in South Africa, can house 250 people, about 800 kilometers from Cape Town. Just some new roads we put in. On the left, we've had to put in a low-frequency radio communication system covering the full site, operating outside the observing bands of the telescope there, but that's for safety purposes. We're building this in the middle of Meerkat. So we have to be very conscious that Meerkat is an operational radio telescope, and we work very carefully with the South African Radio Astronomy Observatory to minimize any interferences that we might put in place. This is the footings for a foundation dish foundation going in. There's the second dish being prepared for its big lift. The lift has to be done under good weather conditions. You can't have significant wind for obvious reasons. Because of the remoteness of the region, we've had to provide full paramedic emergency response, purchase and equip 2 quite sophisticated ambulances, done the same in Australia as well, of course. We're surrounded, there are 4 fairly remote farming communities in the vicinity of the telescope site. So we keep those communities well informed as to what's going on. And in fact, we're employing significant number of people from those communities. There's very high unemployment there. And we've been able successfully, I think we have 130 contractors from these communities working for us, which I think is excellent development. And just showing you the prototype receivers, which are being prepared to go on to the first few dishes within the next couple of months. Moving across the Indian Ocean, this is our team in Australia. We're actually up to 76 staff now there. It's slightly more people we've been able to get employed. And here is the equivalent SKAO construction camp, which is fully operational. It's very pleasant, both are pleasant places to stay. They have to be in these remote regions. Again, evidence of construction. This is a trench being put in easy ground, but we've hit granite. We knew we would. We knew the granite was there. We've now hit it, so this beast is being deployed to cut through the granite. You have to build contingency into your budgets to deal with the ground circumstances as you find them. And you can see this one is looks like it's putting some blue fiber cable, pulling that behind it. Challenging conditions to work in. We Brits think it's hot here. It's hot there. That's not right now because it's winter. But yeah, we have to be very careful, look after the welfare of our people on site. This is the core of SKAO, and that's a kilometre across, just under. It's about 950 meters. When I went on it recently, I was just blown away. The scale, it brought home to me the scale of what we're doing out here. 9 months ago, this just looked like the bush that you see behind it. But in a couple of years, that will be full, absolutely packed solid with ground screens and SKAO antennas. And it will be a magnificent sight to behold. We have time-lapse camera set up, so hopefully we can record the change as this is built out. The area in the center there is Aboriginal heritage area. There's some Wajiri Yamaji artifacts in there. So our agreement with the Wajiri is that we avoid areas of cultural significance to them. So we don't go in there, we'll leave that pristine. But the rest of the area, they declared as being fine. This is the first remote processing facility, which contains beamformer, electronics, control systems, and the like for a group of stations. I think we now have 3 of these remote processing facilities on site. Obviously shielded containers. We don't want to be our worst enemy. So you can see the developments there. That's the very first SKAO antenna going onto the steel mesh, which was on the 7th of March. And under very close supervision, I put 2 of the screws into that antenna, just to say, I helped build it. And Xavier mentioned ALMA. We have much less sophisticated antenna transport systems, Xavier, out at SKA. And these are built in Italy, these antennas from a company called Sirio. So Sirio has the contract to deliver all of the SKAO antennas. So a little piece of Italy sitting out there in Western Australia. We have challenges, all of those that have struck every other project in this stage. We started construction right in the middle of COVID, which was a challenge in itself. We've been hit by inflation, labor shortages, supply chain, shipping costs, etc. This has placed pressure on the budget. As Xavier said, the budget's very tight, but we're working very hard with the members to solve it. Spectrum management issues affect us. I'm sure you're all aware of Starlink and OneWeb and the Amazon systems. There are quite a few other constellations coming. And this is a 2-hour snapshot of the sky from a national park just north of where our site is. And almost every stripe you see there is a Starlink satellite. That's in the optical domain. The radio domain, each one of those is a moving radio source as its downlink to the ground stations, links up with the ground stations. So we're working very closely with the companies so they don't beam onto the SKA telescopes. But it's a long-term challenge. So we sit within the UN Committee on the Peaceful Uses of Outer Space and the International Telecommunication Union, Big World Radio Conference in 2027, all of these to try and put the regulations in place. We also have the myriad daily issues that result from building one of the largest science facilities on Earth. My construction director in Australia tells me that the way to break a drought in Australia is to build a telescope. And we had a lot of rain there in the last 2 weeks. And this is what we have to cope with. It's dried up now. We actually had to use a helicopter to bring in food because they were down to the last 4 days of food. But we normally don't use a helicopter. But anyway, it's dried out now and we're back to normal. But the picture on the left, that's one of those big tractors stuck in the mud. So you can see the challenges there. So level of risk has increased, but we're managing it. Construction activities, I hope I've convinced you, are proceeding at a fantastic pace. First light expected this northern summer, and we're on our way to science. So hopefully at some point in the near future, we'll be able to show science results as the previous 2 speakers have done. Thank you very much.
Thank you. Thank you. That looks very challenging. I hope everything is fine. Any questions? One quick question we have time for. Or you can maybe grill him afterwards in case you're not hot enough, warm enough. Okay, so the next part is the 2024 Astronomy and Astrophysics Awards for Best PhD Thesis and Early Career. And I would like to invite the chair of the board of directors, Arunas Kucinskas, and Thierry Forveille, who is the editor-in-chief, to present those awards. Come on, gentlemen, please. I would ask the awardees as well to come in for the awards. You announced them.
So I'm very pleased that the European Astronomical Society invited us to give the awards, the ANA awards to our awardees in its General Assembly. So the 2 awardees this year work on very different topics. The first awardee for the ANA PhD article award is Mohammad Farhat from Paris Observatory. And going on to a fellowship at Berkeley, fairly prestigious fellowship, I must say. And his work is actually at the interface between astronomy and geophysics. His work in that article. That article looks at what's actually a very old problem dating back to the Apollo mission time, which the Apollo mission allowed to measure the distance to the moon to a few centimeters by sending laser beams to reflectors on the moon. And ever since those measurements started coming, we've known that the Earth-Moon distance is changing too fast. Too fast in the sense that if you input the current rate into models of dissipation, you find that the Earth and the Moon were a single body just 1.5 billion years ago. So that's about a third of the age of the solar system. So clearly, something is a problem. And it actually means that the current rate of dissipation is about 3 times higher than its average over the long time. So people have been looking at that for a long time, looking at various options. And Mohammad found the solution. The solution actually is in the oceanic part of the tides. The tides have 2 components, the solid current tides and the oceanic tides. And the solution is in the oceanic tides. That's something people had, of course, looked at, but that not taken into account that the Earth's continents move. And if you take that into account and look how oceanic tides change depending on the configuration of the Earth, whether it's our current configuration with 4 or 5 continents or the configuration some 50 or 100 million years ago with a single continent, it changes the oceanic tides by quite a lot. And in particular, using a simplified model, Mohammad showed that the Earth-Moon system has crossed a number of resonances, and at those times, the dissipation of the Earth-Moon system was very different from what it's now. And if you look at, if using his simplified model, he's essentially solved this very old problem. And for that, I congratulate him. The second prize is for an early career researcher, so not for a PhD paper, but for somebody who's within, I think, 5 years of their PhD, and is to Michael Romano, who's initially did his PhD here in Padova, but who's now on a permanent position at the Nuclear Research Center in Poland, in Warsaw. His work is on essentially at the other end of the distance spectrum, working on issues in galaxy formation at high redshift. The issue he looked at in the paper that got him the prize is the importance of mergers as contributing to the assembly of galaxies at redshifts above 4 or so. The problem, mergers, of course, are well known to be a significant contributor to the assembly and evolution of galaxies, together with accretion onto galaxies. But their importance at high redshift was unsettled. And the reason for that is that identifying mergers just from images, from morphology, becomes increasingly difficult and unreliable when you go to higher redshifts. So to work around this problem, he used ALMA observations where he had access not just to morphology, but also to kinematics, and that allows identifying mergers a lot more cleanly. Doing that, and also using baseline of literature measurements at lower redshift, he showed that the number of mergers increases steeply with redshift until a peak at redshift about 3, and then drops off fairly slowly above those redshifts. That does not, unfortunately, fully solve the question of how quantitatively important mergers are, because what the information he had access to through his measurement is the number of mergers, but that doesn't give you the rate. To get the rate, you also need a time scale, and that time scale, unfortunately, is hard to measure observationally. So if you adopt the time scale from the simulations, which is what people have to do and what everybody does, then mergers make a very a very significant contribution at high redshift. And for that, we congratulate Michael for this excellent work.
So on the board, on behalf of A&A Board of Directors, it's my utmost pleasure to congratulate you on the achievements that you made, and we are at A&A. We are really happy that we have people like you publishing papers in our journal and doing significant contribution already at the very first steps in your career. That's truly amazing that you are very happy with that, and congratulations to you for your work and for your achievement. I would also like to add a few words for those of you, our younger colleagues who are here and those of you who are not here. At A&A, our main goal is, of course, to publish one of the best journals in astronomy, and at least in terms of impact factor, we are the best. But also, we know that you, our younger colleagues, you are the future. And although, as I said, our main goal is a journal, but at the same time, we are very happy that we can somehow, at least, even in a small way, to really encourage you for what you do and for what you achieve. So with this, I would like to remind you that next year, you, our younger colleagues, that's your opportunity. And we have these calls for the awards. So the way it works, you have to apply for that. And we have calls for the awards announced normally in October, and the deadline is sometime in November. Normally, again, end of November. So please do apply. Look into that and apply, because this is your opportunity to be here and to really tell us what you have done, and that it's, of course, on our side, it's a pleasure to congratulate you. So thank you very much. Congratulations again.
Yeah, congratulations. I can give you each a couple of minutes if you would like. Yeah, go. That's your moment. Come on.
Thank you for that. Yeah, so thanks, Thierry. Thanks, Arunas. Thanks, ANA, and thanks for the board of ANA, and for the selection committee that gave this award. On a personal note, of course, credit is due to my PhD advisor, Jacques Lascar, and the interdisciplinary team at the Paris Observatory of mathematicians, astronomers, and geoscientists, as Thierry mentioned, who really made my PhD work possible. Yeah, so it's only a few minutes, so I don't have a time slot for more details on my work, but as Thierry mentioned, it's really My PhD work was really a dedicated study on the geophysical evolution of the Earth's oceans, atmosphere, and interior, and the associated dynamical, orbital, and rotational evolution of the Earth-Moon system. So after the plenary works of the exciting exploration of the outskirts of the solar system and exoplanetary systems and large structure surveys, it's really satisfying to receive an award for a work on the Earth-Moon system because there's still much richness to be addressed in this system. So thanks again, Thierry, Arunas, and ANA. Thank you.
So hello, everyone. I will be very brief. This is lunchtime. I just want to thank everyone and also the board of directors of A&A for this award and EAS for this invitation here in Padua. I feel very happy to be here because this was the city where I got my PhD and I started my scientific career in astronomy. And I will take this award as an opportunity to continue my investigation of galaxy evolution at high redshift and across cosmic time. And in this regard, I also would like to thank my PhD supervisor, Paolo Cassata, and the whole Alpine collaboration that allowed this work to happen. So I will not take more time. Thank you very much for this award and enjoy the last few hours of EAS here in Padua. Thanks.
Congratulations to both of you again. And now I'm giving the microphone to Lex for the closing ceremony.
Thank you. Excellent. Congratulations. So good afternoon. My name is Lex Kaper. I'm the Vice President of the EAS and I have the honor to chair the organizational board of this meeting. I think it has been a wonderful week, and although the scientific program is not ending now, of course we have two more sessions in the afternoon. We have now reached the moment of the formal closing of the meeting, the closing ceremony, which I'm happily chairing at this moment. So there are a few things that we have to do. There will be the announcement of the poster prize, the ePoster prize winners. And we will, of course, look back onto the organization of this meeting and, of course, shed some light on the meeting in next year, in 2025. So let me first reveal the secret of who has, according to us, the ones who voted, created the best ePoster. I think I should say one thing about the ePosters. This is an enormous amount of work that people put in that to be present at the meeting, to be able to share your scientific results with the people that are present here and also online. Still, I think that we could do a better job in giving more exposures to the ePosters. But that is, of course, a challenge. We do our best. Any suggestion, of course, from your side to even further improve on that is very welcome. So please come to me. But now, let's now concentrate on the three best ePosters that have been shown on display here. The third prize, which is actually two books from Springer and Oxford University Press, goes to Alberto Flores from INAF, actually in Padova in Italy. I don't know whether Alberto is here. If so, of course, he could stand up. We should congratulate him. His poster was on chemical abundances along the quasar main sequence, and the two books are available at the reception desk until the end of the day. And so I hope, of course, Alberto is in the position to pick them up. Now, for the second prize, three books from Springer and Oxford University Press go to Logan Francis from Leiden University in the Netherlands on the molecular and atomic component of outflows from protostars probed by JWST MIRI. Congratulations, Logan. And then the winner, which is also receiving a prize, of course, including actually free ticket for the dinner, the conference dinner in Cork, and that is really an experience, as you have all seen yesterday evening. So that is a real prize. The winner is Sophie Rozou from the KTH Royal Institute of Technology, Stockholm, Sweden, on apsidal motion in massive binaries. So congratulations, Sophie. Sophie is there. Sophie, please come forward if you want. Show yourself in this way. That's awesome. Congratulations. And as I said, the book is available till the end of the day from the reception desk. And I hope, of course, to seeing you at the conference dinner next year in 25. Okay, so having said that, it's now my great pleasure to introduce to you our new EAS president, Sara Lucatello.
Good morning. Well, good afternoon. Like Lex said, rightfully, it's past noon. Colleagues and friends, as we're wrapping up this fantastic week here in Padova, I'd like to share a few words. There are going to be a few because I realize I'm standing between you and lunch, and take the opportunity to thank the many people who have made this meeting possible. This has been a fantastic meeting. We've had over 1,800 participants, almost 1,600 here on site. This is a quite remarkable meeting. 15 symposia, 49 special sessions and lunch sessions, over 1,000 talks, and almost as many posters. As you all know, Padova enjoys a special relations with astronomy. Galileo Galilei did some of his groundbreaking work while living and teaching in Padova, and today the city hosts institutions that do cutting-edge research on a wide variety of astronomical topics. And this week, thanks to this meeting and to all of you, Padova was the world capital of astronomy, in fact. The program of the meeting has showcased some of the best astronomy and research that is done in Europe, but beyond as well. We've heard from small solar system bodies all the way to the high redshift universe, with a very healthy sprinkling of discussion on instrumentation and planned facilities. And of course, we've had some other topics that, even if they're not strictly relevant to the science themselves, they're quite important to our life, like equity, diversity and inclusion, the support of early career researchers, and public engagement. And we've also had an astronomical themed concert, which I hope you all enjoyed. It was quite spectacular. I hope you've taken advantage of this program. I hope also you've taken to heart the suggestion that Roger gave during his opening speech, and you enjoyed a little bit of the wonderful art and culture that the city has to offer. To me, one of the most exciting aspects of this meeting has been the participation of young researchers. 1 in 5 participants is a student here, and there are even more postdocs. And about 50% of our participants are early career researchers, which is unusual when you consider what the general public and large astronomical conferences look like. This is something that we, the EAS Council and the EAS Board, are very proud of. To you young participants, I say, I would encourage you to get involved, propose for a session next year. Do not hesitate. This is an opportunity for you. We really love for you to get more involved. Also consider joining one of our advisory committees. Consider also getting in touch with council. If you have suggestions or comments, we'd love to hear from you. After all, you're the future of astronomy, so your input is crucial for us to move forward. This year, we've had, for the very first time, a fully hybrid meeting. This has been something that is important to us. It has enabled participation for people who are not in a position to travel to Padova. However, this implies considerable commitment of resources. And as we move forward for the future and plan the future meeting, it's very important for us to make informed decisions. So I do encourage you to provide feedback in our post-attendance survey that you'll receive a link for in a couple of days. Your input will inform our decisions in the future. So please let us know what you thought about the online participation. And now a few thanks, more than a few. So I would like to start by thanking the participants and organizers of the sessions. The discussions that have been going on, the science ideas have been the true lifeblood of this meeting. So please let's give a big thank to all the participants and session organizers. Of course, our sponsors and exhibitors have had an instrumental role in making this happen. We couldn't have done it without you. You really help us put this all through, and we're very grateful. In particular, I would like to acknowledge the contribution of ENAF, because ENAF has not only generously supported the meeting overall, but has allocated specific funding to supporting the childcare and the hybrid component of the meeting, making it easier for people to attend the meeting. So let's give a big thank to ENAF. The president is the first row, Roberto Ragazzoni there. Thank you. Naturally, a shout out to the annual meeting board. It's a group of people that brings together some counselors, plus the hosting committee and the local, and CONI, of course. And they've been working year-round to make this meeting happen. They will start working for Cork in just a few weeks, so we have to give them a big thanks for all of us. Of course, the SS co-chairs have had the task of putting together the program, of selecting the sessions, and of coordinating the General SOC. We're very grateful for their work. Bianca Boggianti should be in the room. Unfortunately, Giusy had to leave early, but we'd like to thank them very much for their work. Now, a truly massive thank you to the volunteers, the people in the bright shirts that have been making sure and working tirelessly to make sure that everything went on without a hitch. You've been fantastic. Thank you so very much. Big round of applause for them. And now I'd like to extend a special thank to Kwoni Tumblara, our partner. I'd like to call to the stage Frank, Adela, Lori, Fedor, Marta, Yaria. They've been our partners for a long time. And they worked very hard with us, and they make sure when we're attending the session, when we're having lunch, during a conference dinner, that everything is under control, that they take care of absolutely everything. We're extremely grateful to you. And we have to celebrate the 10th year of collaboration with Kwoni. It's a long time. We have a small gift. I don't know who has the book. Okay, volunteer to present. This is a book written by a local professor in Galileo and Stars in Italian and English. And we're presenting it to Frank, as he's the one who's been with us for 10 years. So thank you so much, Frank. So last in this list, but very much not least, our hosting committee, that I'd also like to call to the stage. Alessia Moretti, Marco Guglielzi, Simone Zaggia. Please come to the stage. And also please, Elisabetta Rigliacco, who is not one of the hosting committee co-chairs, but she's been coordinating the volunteers masterfully. I hope she's here. Oh yes, here she is. Okay, thank you. They've done a fantastic job. They've been engaged in everything from the social events, the science program. They've been on top of everything, working since, okay. Starting at 7:30 a.m. in the morning, being the last one to leave at night. So we owe you a big thanks. And we have a small gift for the co-chairs of the hosting committee.
Thank you.
Yes, sorry. Just for the hosting. Thank you. As you all know, Roger stepped down during the GA just a couple of days ago, after 7 years as president of the society. What many of you, however, might not be aware of is the tremendous growth, both in size and in stature, that the society has enjoyed under his leadership. The number of individual members have quintupled. The number of affiliated societies and organizational members has also considerably increased, making the EAS a true pan-European organization, something we're very proud of. He's also, thanks to his vision, he's also successfully guided us in interactions with the European Parliament, the European Commission. We've had, under his leadership, we've gained permanent membership status at the UN Outer Office for Space Affairs. So we had a number of incredible successes during his tenure as president. Roger, if you could get on stage one more time. We now have a small gift on behalf of the council. I know you've been giving a gift on behalf of the membership, and we have a gift on behalf of council. Thank you. I know I'm speaking on behalf of all the council, that we all think that serving under you has been a privilege and a pleasure. And we wish you a lot of luck in your future endeavors, and we will miss you. And now back to Lex.
So thank you, Sara. Thank you all for joining in thanking the people that made this all possible. I have a very pleasant role of chairing such an organizing committee, and that all the people do the marvelous work to make this meeting a success. And now, of course, for the next meeting, it will be, of course, very difficult to make the meeting even better than the one we have, but that is, of course, our goal. So I would like now to invite both the hosting committee of Padova and the hosting committee of Cork in Ireland. You were, of course, already well aware. Paul and Matt, perhaps you could come over here. And so we do the moment that you will see actually this summer many times of handing over the flag to go from one city to the other. And so here is the flag. And so Matt isn't here. So well, Paul, you're fine, of course. So this is... So before this official closing ceremony ends, let's hand over the responsibility of organizing the EAS annual meeting from Padova to Cork, and hope to see you all there. Yeah. I wish you all a pleasant lunch, a successful ending of the scientific program of the meeting, and a very healthy and good trip back home. See you next year.
questions and questions what I knew